Okay, that's great. So okay, briefly, okay, so for displacement equation, it is actually based on the amplitude, yeah, the y component of amplitude, okay, and that's the equation, yeah, a equal to y equal to a sine omega t, and we get a sine curve, yeah, and then for velocity graph, actually is based on tangential velocity. Okay, tangential velocity is actually the y component of tangential velocity, and this is the equation we get, velocity versus time equation, which is a cosine graph. Then we will get a cos graph. Okay, I will draw the graph for you and see. And then acceleration is based on centripetal acceleration. Centripetal acceleration, and it is also the y component of centripetal acceleration. And we get a acceleration time equation, which is a sine equation. Yeah, you will get a sine graph. Okay, so here it doesn't show the graph. Okay, I will draw it for you. Yeah, I will draw it for you. Okay, so let me write out. Yeah, you only have the sine, the displacement equation graph. Yeah, so how about the velocity graph and acceleration graph? So I will draw it out here for you. So this is actually the, you know, the SHM equation. Okay, equations. Actually, before this, I already have all the, you know, your videos, but these are all methods. Yeah, they use you know, they use differentiation to get the displacement equation, velocity equation, acceleration equation. If you look to my old videos, the old syllabus actually use differentiation. They are not using like amplitude. Amplitude, yes, they use the y component amplitude, but for velocity, it doesn't use differentiation. They use tangential velocity. The y component of tangential velocity, and then acceleration, they use centripetal acceleration, the y component of centripetal acceleration. Okay, this is new syllabus. Old syllabus, they use differentiation. Yeah, from displacement equation, differentiate dx dt, we get velocity equation, and then differentiate again, we get acceleration equation. That's the old syllabus. Okay, but new syllabus require you to use the real concept. Yeah, tangential velocity and centripetal acceleration. Okay, so that's why I'm recording the videos again. Yeah, so all right, let me write out the equation again, but the equation actually is the same. You still derive out the same equation. Yeah, you still derive out the same equation. So I want, and last time the symbol is x. Yeah, last time the symbol is x. Now we use y. We use y. Yeah, because we treat the, you know, the displacement like, because the displacement is actually the y component of the amplitude. So the displacement we put as y, so that no confusion happen. Yeah, if we put as x, it becomes like x component of amplitude, which is a bit weird. So we use y component of amplitude. That's why we put displacement as y. Okay. So so how many equations we have already? 3 equations. Still remember the 3 equations? Okay, let me show it for you. Displacement equation, displacement time equation, a sine omega t, and then velocity equation, velocity versus time equation, omega a cos omega t, and then acceleration time equation is you know, negative omega square a sine omega t. Okay, this acceleration time equation. So let me write it down for you. So we have displacement time equation already. So which is you know, y equal to a sine omega t. Yeah, I just want to summarize out. So velocity time equation is you know, v equal to a omega cos omega t, and then we have acceleration time equation. Yeah, acceleration time equation, which is negative a omega square sine omega t. Okay. So that's it. And then how do we draw the graph? How do we draw the graph? So if you want to draw the graph, then we need to separate a little bit. Okay. Yeah. Separate a little bit. So, oops, sorry. Okay, so let's say for the first equation. So how do we draw the graph? How do we draw the graph? So it is a sine graph, isn't it? Let me oops, yeah, it should be okay. Sine graph is a sine graph. Actually I shouldn't, you know, sorry. So it's a sine graph, yeah. Wait a second. Okay, so we have you know, the displacement versus time equation, and then we have velocity time, and then we have acceleration time. Do you know how to draw their graph? Very simple mathematics. This is based on trigonometry, you understand? Trigonometry. So if a sine graph means it looks like
an S.
Sine, yeah, it's a sine. Just draw a sine graph. Okay, where the maximum is amplitude. Okay, so for this, the y maximum is a. Understand? And then the rest, how about velocity graph? Is a cosine graph. Normally we do draw two wavelength lah. Yeah, we draw two wavelength. Like that. Okay. Just now here, here is considered as one period, two period. From this one to here is one period. Here to here is two period. Okay. Can you see that? So this is a omega. That's my maximum value. Negative a omega. You know, this is the maximum value here. Maximum. Okay. Maximum value. And then this is a cosine graph. So the V maximum is a omega. The V maximum is a omega. Okay, and then the following is a negative sign equation. Negative sign is invert of this sine graph lah. Invert. Yeah, make it invert. So invert, so it becomes like this. Okay. Okay. So this is a period. This is a two period. Okay. What's the maximum value? Can anybody tell me? A omega square. A omega square. So the maximum acceleration is a omega square. Okay. Maximum acceleration. You know about this value? How to find no, the maximum displacement, maximum velocity, maximum acceleration. This is to calculate the value lah. Yeah. Still remember the you know the where is our simulation? See there? This the simulation. Remember that? This is simulation. Okay. Sekarang we find this is the maximum, the blue line has maximum amplitude, and then the orange line maximum velocity at the center. That's a omega. You know, that's a omega to calculate the value. And then maximum acceleration is a omega square. You see that the red line is maximum at the amplitude. You know, where is it? This one, see that? When at amplitude, it has a maximum acceleration. What is the value? What's the value? A omega square. Okay? Understand? That's it lah. Okay. The unit of this displacement is meter, velocity is meter per second, and then acceleration is meter per second square. Okay. So now we have displacement time, velocity time, and acceleration. Acceleration time equation. That means if we give a time, let's say I want the time at 2 seconds. So what is the displacement? If time at 3 seconds, what is the velocity? If I get time of 4 seconds, what is the acceleration? Understand? So this equation is, if you give time, you can get the displacement, you can get the velocity, you can get the acceleration if you give time. Okay, but there's another equation, another two equation with displacement. That means this is velocity versus time. How about the equation of velocity versus displacement? There's another equation also. Yeah, this is velocity versus time. We also have equation for velocity versus displacement. We also have acceleration versus displacement. Actually, I discussed all that already. Yeah, acceleration, displacement, velocity, displacement. Yeah, already. But now it's new thing. Yeah, new. Just a new symbol. Yeah, instead of x, we use y. Yeah, instead of x, we use y. So let's look at the notes. Yeah, let's look at the notes. Okay. Everybody okay? Are you okay?
Yeah.
Okay, let's look at first of all, we look at the velocity displacement. Velocity displacement, yeah. How to get the equation? So we use Pythagoras theorem. Okay, this is use a bit different from the hold on a second. Okay, look at this velocity versus displacement equation. So if you look carefully, this right angle triangle is just like this right angle triangle. You understand? This is amplitude. This is the y component. And what is this? Want to write something there. Sorry. Hold on a second. Okay. Still remember last time you learned about this one. So how about this side? Yeah, how about this side? Where is it? Okay, how about this side? What is this? This is third a square minus y square, isn't it? Correct or not?
Yes, sir.
Yeah? Can't hear your voice. Yeah? So it is a square minus y square, third. So okay, that's important. And then here we have the tangential velocity. Tangential velocity. Okay, tangential velocity. That is what it means by this one lah. Okay, this is what it means by this one. Yeah, this one is actually the radius. Yeah, this is the radius. You understand? Can you see it? Can everybody see it?
Okay.
Good. Very good. You're all very good. So now we can find what is cosine theta. Yeah, we can find what is cosine theta. Just cosine theta is adjacent over hypotenuse ma. Yeah, adjacent. That means this is adjacent over this hypotenuse. This is the hypotenuse. Okay. It is adjacent over hypotenuse. Understand? Adjacent over hypotenuse. So that's cosine theta lah, adjacent over hypotenuse. Okay, we got it. So why is it important to know cosine theta? Because our velocity time equation, we have cosine theta. Okay. So that's why we need to find out what is cosine theta. Okay. We actually, why we need to know all this? Because we want to find equation of velocity versus displacement equation. We want to find what is the relationship between velocity versus displacement. This equation is velocity versus time. Velocity versus time. This equation, we need to find another equation which is velocity versus displacement, not velocity versus time. Understand? Velocity versus displacement. So this cosine omega t, we need to substitute with displacement. So first, from here we got it. Oh, cosine theta is surd omega square, surd a square minus displacement square over a. So we can substitute the time with displacement already. Do you see that? You can see it, huh? Okay. So too many, too many. Okay, so this equation just now, yeah, okay, this equation, we use it to put it here, okay, so we substitute the cosine theta, yeah, with this, we substitute with this, understand? We substitute with this, and then that's how we get the equation for velocity versus displacement. Velocity versus displacement, you see that? Yeah, you substitute this with this, and then the a can be, when you substitute a and a here can be cancelled off. Okay, a and a here can be cancelled off, and then we get this one lah, plus minus omega square root a square minus y square. So this is a equation of what? Equation of velocity versus displacement. Okay, and he say velocity is maximum at what? At equilibrium. Hence, v maximum is a omega. So at equilibrium, it is maximum. So that means at equilibrium, that means when y equal to 0, we substitute y equal to 0. If we substitute here y equal to 0, what happened? If we substitute here y equal to 0, what happened? It become a square minus 0 square, isn't it? 0 square. So 0 square. So we will get what? We will get positive negative a omega. Correct or not? Third square root of a square, we get a. So that's the velocity equation. Okay, that's the maximum value, a omega. Still remember the equation just now? V max is a omega. Or omega a, you want to put it as a omega or omega a is the same lah. Okay, can you see it? Yeah, a omega or omega. So is it velocity maximum at equilibrium? Is it velocity maximum at equilibrium? Is it velocity maximum at equilibrium when y equal to 0? Look again at the, you need the simulation lah. You need the simulation. Okay, you need the simulation. See the simulation again. See, at equilibrium it is fastest. The block is the fastest, kan? You see not? At amplitude it stop for a while, but at equilibrium it is moving at the fastest speed. It has the maximum kinetic energy. Look at the red bar, maximum kinetic energy and maximum velocity. Look at the orange line. The orange line is longest at equilibrium. And do you know why? I always press the wrong button. And do you know why here got positive and negative sign? Do you know why here got positive and negative? This positive and negative means direction. Means what? Direction. This is called the direction, to the left or to the right. If direction, so it can be, the object can be moving to the left or to the right. If moving to the right is positive, if moving to the left is negative. You see that? Where's my? You see the block? You see the orange line? It can be to the left, to the right, to the left, to the right. So got positive or negative. Do you see that? So the block at equilibrium, the block has two possibility. the block has two possibility. It can either move to the right or move to the left. So at this position, equilibrium, the block has two possibility direction. Direction. It's either moving to the left or moving to the right. Okay. Now you see everything. Yeah. So it's either positive or negative. That means it's either moving to the left or to the right. If to the left is negative, if to the right is positive. Okay. So it has two possibility direction at any displacement. So here we can add one more equation. What's the equation for velocity versus displacement? Okay, let me write it down. What's the equation? So V equal to positive negative omega A square minus Y square. Where what is the V maximum? What is the V maximum? A omega also. Yeah. When Y you put as 0 at equilibrium. So at equilibrium, the velocity is maximum. Okay. Now, but if you put at amplitude, yeah, let's substitute. If let's say y equal to amplitude, what happen? If y equal to amplitude, what happen? Yeah, let's calculate. Let's find it out. If the object at amplitude, look at the simulation. If the object at amplitude, what happen? Object at amplitude, velocity become, look at the orange line become 0, isn't it? So velocity becomes 0 at amplitude. The kinetic energy also become 0. See that? Kinetic energy, the red bar becomes 0. So at amplitude. Look at the derivation. When you know, so at let's say y, let's say at y equal to amplitude, what happened? At y equal to amplitude, so v equal to positive negative omega a square minus a square. See that? Where at amplitude, the y amplitude, so a square minus a square, what do you get? 0. 0. So velocity is how do I write? So I can write okay. So velocity is minimum 0 when y equal to amplitude. That means this one is at amplitude. It stop for a while, you know, it stopped for a while and change direction. It stopped for a while and change direction. Okay. Everything is laid out clearly over here. Yeah. Okay, so how about acceleration? We got the velocity. Yeah, we got already velocity versus time equation and velocity versus displacement equation. Now, how about acceleration versus displacement equation? Okay, let us look at the. Okay, very simple. This one lagi simple. Acceleration versus displacement equation. Acceleration versus displacement equation. We just you know, from the equation, we got acceleration versus time equation is negative sine equation. Yeah, negative sine equation. Negative omega square a sine omega t. Do you notice something over here? Here we have a sine omega t. It is similar to what? Similar to our displacement equation. A sine omega t. Do you see that? A sine omega t. A sine omega t is y. Here, a sine omega t is also y. You understand? Okay. So here you see here a sine omega t. This one we substitute with y. Yeah, because y is a sine omega t. So we substitute it, and then we get this equation. This is last time we have, you know, this is acceleration versus time equation. Now we have acceleration versus displacement equation. Very simple. Acceleration versus displacement equation. So that's it. So we can add one more equation, you know. Can add one more Okay, add one more equation over here. We got for our collection, A is equal to negative omega square y. This one, you see. So if y equal to 0, okay, let you tell yourself, if y equal to 0, what is A? If y equal to amplitude,
Zero.
yeah, very good. If y equal to amplitude, what is A? Negative omega square A, isn't it? So, hey, this is, what is this? Do you realize what is this? What is this? Do you remember? Have any memory of this? Do you have any memory? A most important equation for SHM. See that? That's the meaning of SHM. That's the definition of SHM. Yeah, back to what I said before. When displacement, acceleration and displacement, they are proportional. If displacement increase, acceleration also increase. If acceleration 0, if displacement 0, acceleration also 0, and they are opposite direction, negative. Acceleration and displacement, they are opposite. They are, you see, they are proportional. Acceleration and displacement, they are proportional yet opposite. Okay. Their acceleration and displacement, they are proportional yet opposite. Okay. This is the meaning of the definition of SHM. Okay, understand? So this one, acceleration, can write lah. I can write another notes here. So acceleration maximum, which is equal to let's say like if negative omega square A when when y equal to actually just put the value lah. We don't want the direction. Yeah, we don't want the negative sign. Just the the magnitude. This one also just now is the magnitude only. Yeah. So when y equal to amplitude. So and then A is minimum 0 when equilibrium, at equilibrium. Understand? Okay. So we got all the equation already. 5 equation. Yeah, we will use this later. So okay, let me look at next. What do we have? Potential energy. Okay, potential energy versus displacement. So consider the oscillation of a spring as a HHM. Hence, the potential energy of the spring is given by this. So this is a potential energy of spring, yeah, or elastic. Yeah, this is actually the elastic potential energy of spring. Elastic potential energy of spring is half kx square lah. Yeah. But we use, you use y. Yeah. We use y because displacement for equilibrium. Yeah. Because why you use y? Because it's the remember, it's the y component of amplitude. Correct or not? Remember the y component of amplitude. Okay. So we this is the usual formula. Half kx square is the usual formula. Elastic energy for spring, the usual formula we see. Now we change it to y lah. Just x change to y. Okay. And then k equal to m omega square. Yeah. How do we get this k equal to m omega square? Some of you may ask, how do we get k equal to m omega square? Good. Yeah. Actually, this is okay. Last time I did write somewhere. Where did I write? Let me think of it. Where is it? Where do I write? Let me hold on a second. Okay. Look at. So what is exactly this one? Yeah, you may ask, kan? What is exactly where? How do you get that? Okay, well, if we look back, you know, look back to which part? This part, yeah. Hooke's law. Remember the Hooke's law? I need to rewrite over here so that you can see. So Hooke's law. You know, Hooke's law. Okay, Hooke's law is what? The spring force is equal to negative kx, kan? But this one we use k, y, yeah. Our displacement is y. Okay, and then look at here. This is no total F equal to ma. You know, we want to find the resultant force, kan? Total F equal to ma. And then we can say total F equal to ma. So for this spring mass system, the only force is the force of the spring. The force of the spring, understand? Force of the spring only, yeah, acting on the block. So force on the spring we put inside. So force on the spring we put inside. Force of the spring we put inside, which is equal to ma. Understand? Okay. Force. The only force is ma, and then here we have you know, Fs is equal to negative ky. Okay, invert it. Inverted ma is equal to negative ky. Okay, so here acceleration is equal to negative k over m y. And then we compare with what equation? Compare with this equation, the SHM equation. A equal to negative omega square y. You know, actually this chapter is you may see maybe you don't like the derivation part. Yeah, maybe you don't like all this derivation part. Actually the question, I think they won't ask about derivation. They will actually, based on my experience in the past, this chapter just asks how to use this equation only. So we haven't reached that part yet. Okay, right now I'm just, you know, teaching the concept from the scratch to you. Okay, but what will be tested later on is not the derivation part. What will be tested on is how you use this equation, how you use the available equation, substitute the value to solve the problems. So it's just use equation later on. Okay, so don't bother so much how to derive everything, yeah. But because, you know, as a lecturer, I like to teach complete knowledge, yeah. Okay, so back to this one. Okay, so a equal to negative k over my. So, and then with this definition of simple harmonic motion, okay, we can combine them. So combine them with you know, combine them with a equal to negative omega square y. Can you see the magic here? K over m is omega square. Compare them. So from here we get what? We get omega square equal to k over m. Agree or not, class?
Agree.
Very good. And I want you to see there are two things you can get from here. First is k equal to m omega square. And this is where is it? See that? So now m, you substitute, you multiply to the top, you get k equal to m omega square. That's how you get a k equal to m omega square. Okay, and then the other thing I want to show you is omega actually is 2 pi over period. Correct or not? So we substitute that. 2 pi over period into the omega. Okay, and then we square root both sides. Yeah, we square root both sides, so we get square root both sides, so we get, correct or not? We square root both sides, we get this. Correct or not? Correct or not, class?
Yes.
And then very good lah. All of you are very good student. Yeah, and then we we invert them. Understand? We invert them. Invert both sides and then multiply to the top. This is the formula that you use in SPM. Remember that? The period for the spring mass system. Yeah. This is to find the period for spring mass system. The higher the mass, the longer period. It oscillates slower, the higher mass. If let's say the spring is very stiff, spring yang keras. Kalau spring yang keras, dia oscillate apa? Dia oscillate cepat. Dia oscillate dengan laju sebab spring dia keras. Tapi kalau mass yang besar, dia oscillate dengan perlahan sebab period dia panjang, ya. Dia oscillate dengan perlahan, ya. Kalau mass itu sangat berat. Ini you guna masa SPM. Masih ingat? So what I can say is these two formula, they are the same. Okay? Okay? So if you see this, actually it is this one. So this is actually the same formula as this. Okay? So now you know K equal to M omega square. So the spring mass system is half kx squared, which is half ky squared. So we substitute the k with m omega squared. We substitute the k with m omega squared, and we get the formula for potential energy versus displacement. Well, today just learn about derivation also enough lah. So, okay. Wait. We have 2 hours, isn't it? The next hour we discuss tutorial. Okay, but I will let you take a break for a while lah, yeah. I'll let you take a break for a while. So, okay. So, displacement. Displacement versus... this potential energy versus displacement. So, we have another equations. So, potential energy versus displacement equation now we have. So, it is, is potential energy is equal to... Actually, this is elastic potential energy, yeah. Elastic potential energy. Use US kan. Elastic. This is a... elastic potential energy versus displacement equation. So it is write it as half ky square first, and then it is actually half m omega square y square. Okay, half m omega square y square. So this is between potential energy versus displacement. Okay, and please write it down. K is m omega square. Remember this, K is m omega square. Okay, so what is the meaning of this potential energy? What is the meaning? Back to my simulation. I like my simulation a lot. When you create something, you feel proud. That's it. That's the point of being engineer. Engineer, you create something and you feel proud. Yeah. Not just for the sake of money. I actually didn't get any money from this, but I just the joy of making things successful. So you should experience that kind of feeling also lah. Yeah, when you try to make things. So okay, look at this green bar. I want you to focus on the green bar. Yeah, green bar. Okay, so I want to ask you, when is the potential energy minimum 0, and when is the potential energy maximum? At what position? Look at the green bar. When is it maximum? When is the potential energy maximum? The green bar actually represent what? It represents the potential energy, elastic potential energy in the spring. That's why I put it beside the spring. So, when is the elastic potential energy maximum, class?
At amplitude.
At amplitude. What about at equilibrium? What happened when the spring at equilibrium? Is there any elastic potential energy?
No.
No, because at equilibrium, no extension, no compression. Correct or not?
Yes.
At equilibrium, no extension, no compression. So of course, no elastic energy stored in the spring. So all the energy has transferred to the block as kinetic energy. Do you see the green bar and red bar, they interchange together? Interchange one another? When green bar is 0, the red bar is maximum. See that? When the red bar is 0, the green bar become maximum. They interchange the value. Okay? Energy conservation. We call it energy conservation. Good. So again, potential energy maximum, elastic potential energy maximum at maximum compression and maximum extension. That means at amplitude. But elastic potential energy 0 at equilibrium because no extension, no compression. Good. So that's the concept. So if you use a formula, also we get the same thing. See that? When displacement is 0, what happened to the potential energy? No, displacement 0 means no, at equilibrium. At equilibrium, no extension, no compression. What is the elastic energy stored in the spring? 0. Correct? So, okay, I should write over here. Yeah? Write over here lah. Never mind. Yeah? I write maximum first. Okay lah, never mind, maximum first. So, at amplitude, what happened to the elastic energy? It's maximum lah kan at amplitude because maximum compression, maximum extension. So write it down. Let me write it down beside here. Take a little bit of time, but it's worth it as long as you understand. So potential energy is maximum, which is half m omega square a square. Yeah, when the displacement at amplitude, maximum extension, maximum compression. Maximum extension or atau or compression. I write full lah. Okay, but potential energy minimum at 0 when at equilibrium in the spring. No extension or no compression. Okay, no extension, no compression at equilibrium. At equilibrium. So no elastic energy stored in the spring. Very simple, right? Good. So that's the equation to calculate the potential energy. So we have one equation already. So next time we give you the displacement value. You can get the potential energy value of the spring. Calculate the energy in the spring. Next time you become an even better innovator. You can put value over here as the animation goes. Got value changes over here. Wow, I salute you. I salute you. Teach me, at the time you teach me. Okay, so see, this is the graph lah. See the graph. Potential energy. You see, potential energy at amplitude. At equilibrium, potential energy 0. But at amplitude, the potential energy is maximum, which is half m omega square. A square. Actually, this line is that value half m omega square a square. Just now we we get how when amplitude half m omega square a square, that's the value, the whole value. Okay, now I want to talk about kinetic energy. I want to talk about kinetic energy. So is actually derived from the also very similar. Look carefully. Just now we got already potential energy. This equation of what? This equation of potential energy versus what? Versus displacement. Potential energy of the spring. Okay. Now how about kinetic energy? Now is kinetic energy versus this displacement. Yeah, kinetic energy of the block. Kinetic energy of the block. Yeah, so this kinetic energy versus displacement equation. This one is for the block. How to find the kinetic energy equation? That means this is the green bar, you know. This is the green bar. Where's my simulation? This is the green bar value. Yeah, this is the green bar value. This is the red bar value. The block. You also can find the kinetic energy of the block based on the displacement. Yeah, how far is it from equilibrium? You can find the red bar value. Yeah, here I don't include value because I'm not clever. I don't know how to put value there. Yeah, so I'm not clever. So you need to know how to calculate the value. Yeah, based on the displacement. So how do we do it? How do we do it? So okay, this kinetic energy formula, this kinetic energy versus displacement formula, come from this equation. And half mv square block. The block is the kinetic energy of the block is half mv square, and come from this formula. Do you know how to get this formula? Have you seen this formula? This is actually what equation? Velocity versus displacement.
Velocity versus displacement.
Yes, velocity versus displacement. This is not velocity versus time equation. It's not velocity versus time equation. It's velocity versus displacement equation. So because we have two formula already, yeah, this velocity time and velocity displacement, we use this one. This one, yeah, to derive, yeah. Come from which one? This one, yeah, come from here. Okay. So because you know why we want what v in terms of y, because k equal to half mv square. Yeah. You see, last time is the block kan. This is the spring kan. Spring elastic energy is half kx square. Spring. This is half mv square is the block. This is the block. Yeah, kinetic energy of the block half mv square. So last time the displacement, this one direct, yeah, direct. We have the formula already. Okay, this one half mv square v. We don't want v. We want to change it to y. Last time, spring we directly have displacement, yeah, inside the equation. Yeah, displacement inside the equation. But this one is velocity, so we need to change this velocity to y. Then only we can get the kinetic energy versus y equation. Understand? So we need to change out this v. How to change this v into y? How to change this v into y? We use the v versus y equation. We use the v versus y equation, which is this equation. So just substitute inside. Substitute inside this one. This one into here. Substitute inside. Masukkan ke dalam. Masukkan ke dalam. Maka dapat v sudah tukar kepada y. Maka dapatlah equation of kinetic energy versus y. Okay. So substitute inside. You know where is the positive negative sign? No negative anymore because got square. You see here? Here got square. Here got square. After the square, so the negative sign also become positive. So no more negative sign. Yeah. So no more negative sign. So square. So omega become omega square, and then square root become no more. Square root also hilang. So you get this formula. Yeah, v square. You substitute with this one, then you get this one. So the formula for k versus y is this one. K equal to 1/2 m omega square a square minus y square. Okay. Put into our formula. So we have another formula of kinetic energy versus displacement, which is this is last time this is for spring elastic energy. Now this is for block. Okay. So kinetic energy of block is half mv square, but we don't want the v. We change to y. So it becomes half m omega square a square minus y square. Understand? Understand? Do you see how similar is this formula, potential energy versus displacement, and kinetic energy versus displacement equation? Do you see how similar are they? Similar tak? Sama tak? Similar tak? Similar kan? Yang beza cuma ini a square minus y square. Ini y square kan? Terus, betul tak?
Yes, sir.
Betul.
Sana kamu tengok. Di sini, ini m omega square ini boleh ganti dengan k. Betul tak? So, yang ini you rasa boleh ganti dengan k tak? Boleh. Boleh juga. So, ini boleh, kinetic energy ini boleh jadi half k a square, tapi k ini k besar, ini k kecil lah, ini spring constantnya k lah ya, jangan tersalah so boleh ganti juga ya, macam itu ialah half ky square, inilah half k a square minus y square ya, lebih kurang sama. Okay, sebab k is m omega square. Okay, baik. So sekarang tengok, saya nak you tengok betul-betul. So, bandingkan. Bila itu kinetic energy maximum. Bila kinetic energy minimum. So, macam mana? Tahu? Apa yang berubah cuma Y saja kan? Yang mass, omega, amplitude semua ini constant. Ini semua nilai constant. Yang berubah ialah Y sahaja. So, you ganti sendiri. Kalau Y ialah kosong, apa K dia? Kalau Y itu amplitude, apa K dia? Cuba ganti. Kalau Y kosong, dapat apa? Kalau Y amplitude ialah apa? Kalau Y amplitude, K kosong. Betul tak? Kalau Y amplitude, dia jadi amplitude square tolak amplitude square. So, jadi kosong lah kan?
Yes, sir.
So, kosong ke kinetic energy, kosong. So, kita tulis dulu. Kita tulis dulu di sebelah. So, okay. So, kita boleh kata kinetic energy minimum equal to 0 when what? When y equal to amplitude. Y equal to amplitude. Okay? But kinetic energy maximum, which is equal to what? Half m omega square. Bila y equal to 0, maka kinetic energy maximum, the red bar, remember the red bar? When y equal to 0, so half m omega square a square. So when y equal to 0, this one at equilibrium, this one at amplitude. Actually, this one we put at positive negative amplitude also the same. Yeah, the kinetic energy is 0. Yeah. Just now this one also positive negative amplitude lah. Yeah. You at the right hand side or the left hand side is the same. Yeah. Because you know why positive negative? Because here got square, y square. Kalau sudah square, negatif itu pun sudah hilang kan? Tengok baik-baik. Kalau y di amplitude, is it kinetic energy 0? Kalau y di amplitude, is it kinetic energy 0? Kalau di amplitude, is it kinetic energy 0? Look at the red bar. Is it become 0, the kinetic energy? Kalau di amplitude, ya, betul lah kan? Kita punya formula betul lah kan?
Ya, betul.
Kalau di equilibrium, is it kinetic energy maximum? Equilibrium, is it the red bar full?
Yes.
Yes. Dari mana dia dapat tenaga ini? Ini tenaga kinetic energy dapat dari mana?
Spring.
Baguslah kelas. Ya, bagus. Itulah dia. You dapat sudah ya. So, ini tenaga blok dan semua datang dari spring. Lepas tu, blok pergi tarik dia. Maka tenaga pergi kepada spring. Lepas tu, blok dia ada dia tolak balik spring kan, dia pun bagi tenaga kepada spring, macam itulah. Then spring bagi balik tenaga kepada blok untuk buat dia kinetic energy. Lepas tu blok tarik balik, dia bagi balik spring. You faham lah kan? Susah ya, sebab animation ni laju sangat ya. So tenaga dia saling tukar antara spring dengan blok, ya begitu. So kita kena tahu potential energy spring dengan kinetic energy block dia bersongsang. Dia adalah songsang kalau kita tengok. Dia songsang. Kalau potential energy maximum di amplitude, tapi kinetic energy minimum di amplitude. Ya. Dia songsang. Okay, saya nak kamu tengok. Satu lagi benda di sini. Potential energy maximum apa nilai dia? Apa formula dia? Half m omega square A square kan? Dan ini kinetic energy maximum juga apa nilai? Sama juga, betul tak? Half m omega square A square juga, betul tak? So, ini apa maksud? Tengok balik graf ini. Kenapa graf dia macam ni? Satu orang senyum, satu orang muram. Kenapa? Tengok. Ini ialah, kalau kita tengok, sini ada 3 line kan? Yang orange line is the potential energy line. Yang blue line is the kinetic energy line. The black line is the total energy. Is the total energy. So that means, total energy actually is potential energy plus kinetic energy all the time. Yeah, this conservation of energy is, this total energy is half m omega square A square. You understand? That value, that is the total energy value. This is the actually the what is this? This is the total energy value. That is the total energy value is always constant. I think I should draw it over here lah. Better. I should draw it over here so that I can see clearly. Okay. So we already learned about, this thing, yeah. This very hard to adjust this one, yeah, because it's not iPad. Okay. Okay. So this is the energy, the total energy or potential, the spring energy or the kinetic energy of the block. Okay. And this is the displacement. Okay, so we have 3 graphs. We have this graph. What is this? I'm not an artist. Okay, so and then we have the okay lah, use the orange. We have this. Okay, and then we have this one. No. I don't think. Be professional. Okay, that's good. Okay, so what is all this line? What is all this line? What is all this line? All this graph? Okay, so this is the zero at equilibrium. This is equilibrium. This is the at amplitude. This negative amplitude. So you see. So this the orange one is the kinetic energy. Understand? Because it is a maximum over here, K max over here, correct or not? K minimum at, can you see it? Guys, can you see it? Yeah. Hi, so small, should draw it bigger. No. This is maximum. Here kinetic energy minimum. This is kinetic energy, and then you know what is the maximum value? Never mind. The maximum value is half m omega square A square lah. And then how about the potential? This is the potential energy value. Potential energy graph. Okay, the spring one. So U max is over here. Yeah. U minimum over here, U minimum, U maximum. I want you to look at this graph for a long time. And then you remember. So here is 0 lah, yeah, yeah. This is 0, yeah, 0 over here. So what I can say is, you know, it's like this equation. The total energy is the mechanical energy, you know, K and U is always constant. Conservation of energy. And the total energy is actually half m omega square ma square. So this is like you know, what I can say is like this. So let's say now I will put into it. Let's say at y equal to 0, at equilibrium. Who is maximum at equilibrium? Kinetic energy, isn't it? So kinetic energy is half m omega square a square, understand? Plus potential energy 0, understand? So the total energy is this one. So if at amplitude, at y equal to amplitude of positive or negative amplitude, who is maximum? Who is maximum at amplitude?
Potential energy.
Potential energy. Potential energy is maximum, half m omega square a square. And then kinetic energy back to 0. See that? So the total energy is still half m omega square a square. See that? See that? So I can say this you know. So this line, you know, this line, this is the total energy line. You know, this is the total energy line, and you know, the value for this one is half m omega square a square. Understand? Okay. That means at any time, at any displacement, the potential energy plus kinetic energy always equal to the total energy. The potential energy plus kinetic energy always equal to total energy. Okay, it always constant all the time. Okay, the U max equal to half m omega square a square. The K max also equal to half m omega square a square. You see the K max is K is maximum when potential energy is 0. See that? Yeah. See that? This K max is when potential energy 0. Yeah. U max when kinetic energy 0. That's it. And this is the total energy. This is the total energy value. Yeah, is half m omega a square. So we got one more equation for total energy. One more equation for total energy, which is what? The total energy. One more for total energy versus displacement. I can put it. So the total energy is always you know, K plus U is equal to. I need to you know, adjust the whole thing a little bit down. Oops, wait, let me put it somewhere first. Okay, and then put it somewhere here, and then okay, yep. So this half m omega square a square. Okay, and it's always constant. So we have all this formula already, yeah, right from the beginning until now. Okay, so that's that actually concludes our yeah. We have all the formula here. Okay. Okay, emphasize. Yeah, I explained this already. The relationship between the total acceleration energy with amplitude. Yeah, U is maximum at equilibrium, K is maximum. This one I need you to read on your own lah. And then the graph. Okay, graph also explained already actually. See that? Graph I explained already. This graph also explained already. Period also actually a little bit. Okay, let us take 5, yeah, and then we continue again. Yeah. You want to continue with tutorial questions, or you want to stop right here? Okay. Yeah. Maybe this question, yeah. Which one of the following true statements is true when an object performs simple harmonic motion? Wait. I think I stop record.